We are finally finishing up lesson 1.2. I think this is what, day 6 on lesson 1.2? Something crazy like that. We are finishing the notes that we left off on Thursday. And we first started talking about even and odd functions and symmetry. Excuse me. And I don't know what you guys remember from Thursday, because, it's been a few days since then. But remember, if a function is considered even, it has symmetry across the y-axis. So it has that vertical symmetry. And then algebraically, f of x would equal f of negative x. Okay? If a function is considered odd, it has what is called origin symmetry. I haven't shown you a picture of that yet, but I will today. Origin symmetry, there's kind of a diagonal quadrant reflected symmetry thing. Algebraically, then f of negative x equals negative f of x. So we did A and B on Thursday, and we are now ready to try C. The one thing I will show you, on B, I don't think I graphed it for you. I think we just kind of ran out of time, if I recall. So if I show you the graph here, sorry, I got hair in my mouth. If this was centered, it could be symmetric across the y-axis, but it's not centered, so it's not there. And then symmetric across the origin, and again, I'll show you one here in a moment, but if it's symmetric across the origin, something like this bottom piece of the parabola right here would be reflected and be up in this quadrant as well. Okay? Or, so those diagonal quadrants would have the same stuff going on, and that's not there. So that is an example of not symmetric. Okay, C. Okay, do you remember what we did on these others? If we start not graphically, but algebraically, we're given h of x. First thing we need to find is h of negative x. Every place I see an x, I'm going to replace it with negative x. So that means I'm going to be doing negative x raised to the third over 4 minus negative x squared. Well, what happens when you raise a negative to the third power? Stays negative. So on top, I'm going to have negative x to the third. Denominator, 4 minus, what happens when you raise a negative to a second power? It's positive. So that just goes back to the same old 4 minus x squared. So, what do you notice? It's not the same, is it? There's a difference of a sign here. This is not the same, so at this point, we know that this function is not even, so not symmetric across the y-axis. Next, that was h of negative x. Now we need to check out negative h of x, which, if you remember, that negative h of x is taking that negative and multiplying it by the whole equation, or whole function, right? Now, with a fraction, it looks a little bit different. So a couple different ways we can think about it. One is to do the negative times the fraction, meaning if I just kind of write it out front. So it's the negative of that fraction. Now, how do we multiply a fraction by a negative? Well, okay, distribute the negative. Now, here's the key, though. Do we distribute that negative to top and bottom? Or just one? Okay, so here's the thing about this. If we multiply the top by negative and the bottom by negative, what is a negative divided by a negative? A positive. So at that point, you don't want to multiply both by negative. You pick one. You can either, and honestly, there's 3 ways we can do this. We can pick one, we can multiply the top by the negative, or we can multiply the bottom by the negative, or you can just put the negative out front of the fraction. Okay, so as he said, in the middle. Now, in this case, what would make sense to do based on the other part of this problem. Take it to the top. So if we take it to the top, it's negative x cubed over 4 minus x squared, and these are the same. If these are the same, h of negative x and negative h of x are the same, what is this? It's odd. Now, let me show you the graph. Because I keep telling you I'll show you something that is odd or symmetric across the origin. Well, now's the time. I don't know. Getting a glare on the calculator. And whoops, wrong way. It's as dark as I can make it. Okay, trying to make this readable. Do you see some symmetry here? As I said, it's what we call symmetric across the origin. Now, I like to think of, so take for instance this quadrant 1. If you just take quadrant 1, which is this part of the curve right here, yes? And you flip it down across the x-axis and then over across the y-axis, what do you notice? It matches there, doesn't it? Yeah. Or if I take this piece up here that's in quadrant 2, what about if I flip it over across the x or y and then down across the x? It matches. So the idea when I keep talking about diagonal quadrants should have the same pieces in them, just reflected. That's where we're at. Okay, so that is blurry, I think, but that is symmetric across the origin. Does that give you an idea of what I'm looking for there when we talk about symmetric across the origin? Okay. So let me write this in. Symmetric across origin. Okay. So that's even and odd and symmetry. Be able to look at algebraically or graphically. There's times and places you'll want to be able to do both of them. Okay. Ready to talk asymptotes? Those of you that were with me last year in Algebra 2, we talked about asymptotes. My morning class seemed to think it was right before we went to our extended e-learning. I honestly don't remember exactly where it was in relation to e-learning, other than it would have been second semester. I can verify that one. But so vertical asymptotes, horizontal asymptotes. You guys remember asymptotes? They're like the invisible lines, right? That your graph doesn't touch. If it's a vertical asymptote, it's that invisible line. We usually draw this dotted line. My graph doesn't touch it. If it's a horizontal asymptote, my graph won't touch it as it goes out to the left and right, but it can cross it in the center. Now, we talked about this last year, how to find vertical asymptotes. So vertical asymptotes, places that make the denominator equal to 0. So how do we find them? We're going to set the denominator equal to 0. So anytime you're looking for a vertical asymptote, you're going to set the denominator equal to 0, and your vertical asymptote will always be x equals some number. Okay? We'll practice that here in a moment. Horizontal asymptotes. Horizontal asymptotes, I know I gave you guys like notes on these last year, like on a little formula page or something you were able to use on the test. And it's all about the powers. So if the largest power is on top, then there are no horizontal asymptotes. For example, if you had the function x cubed plus 1 over x squared minus 2x. And I'm writing off the screen. Better? Okay. That is an example where there would be no horizontal asymptotes because where is that bigger power? On top. Because x to the third is larger than x to the second. Okay? If the bigger power is on bottom, then y equals 0 is always the horizontal asymptote. So, for example, if I take that previous problem I had and flip it, it's x squared minus 2x over x cubed plus 1. Now notice the larger power is in the denominator. So that's an example of y equals 0. Okay, so it's all about those biggest powers. Biggest power on top, no horizontal asymptote. Biggest power on bottom, y equals 0. That leaves option 3, which is if the powers match. If the powers match on top and bottom, then we use the coefficients of the biggest power. So, let me give you an example here. If I have y equals 3x to the third over 4x to the third plus 1. Okay, this is my example. What are the terms that have the biggest power? Biggest power on top is going to be the only power on top, right? 3x to the third. What's the biggest power on bottom? The term that has 4x to the third. What are the coefficients? 3 and 4. So that means my horizontal asymptote would be 3/4. Because it's all there about that 3 and 4. It doesn't matter what other terms you have, so this plus 1 means nothing. We could have had other terms on bottom, other terms on top. It's just about the largest powers. If they match, use the coefficients. Okay, let's practice. Determine any horizontal or vertical asymptotes of this given graph. Well, let's start with the order we did earlier. Vertical. How did it say to do vertical asymptotes? Denominator equal to 0. What is my denominator in this problem? Okay. X squared minus x minus 2 equals 0. How do I solve that?
Would you add the 2 over?
No.
Factor.
Factor. And honestly, you could factor before you said equal to 0 if you wanted. So if we factor this, x squared breaks into x and x. What multiplies to equal negative 2 and adds to equal negative 1. Negative 2, positive 1. And then what do I do with those after I factor? Set them each equal to 0. So x minus 2 equals 0, or x plus 1 equals 0. And so these are going to work out to be x equals 2, x equals negative 1. Those are my vertical asymptotes. Now, let's talk about horizontal. Any thoughts on horizontal? Bigger powers where? On the bottom. So what's that mean? So y equals 0. So the biggest power on top is x to the first. Biggest power on bottom is x to the second. So that right there, biggest power on bottom. And so that does give me a horizontal asymptote of y equals 0. Now, I do want to take a moment and look at this graph. On your own, you guys are not at the position where you can graph this on your own. Okay, but I want to take you through some things and look at how we can graph it by hand.
This is probably a good question. So the biggest power is always on the bottom, then it's always like.
Yes.
Got it. That's key.
Yep.
That's like easy.
Yeah, if there's no, okay, how much bigger is the bigger power on bottom, or no, just bigger power on bottom, y equals 0. Period, end of statement. Okay, so I'm going to sketch a graph in here. I don't know if you guys have room for this or not, but what do I know that I can go ahead and label on this graph? Is it my x and y axis? Okay. Can we put in our asymptotes? Yeah. Where are we? We're supposed to have vertical asymptotes at 2 and -1. So remember to draw a vertical asymptote, I just tend to do a dotted line here, or dashed line. So that means my graph is going to jump over those places, right? It's not going to cross through those vertical asymptotes. There's also an asymptote, a horizontal asymptote at y equals 0. What's a horizontal asymptote? Or what at y equals 0? I guess what I'm trying to go at, where is y equals 0? It's the x-axis, right? So we're also going to have this horizontal asymptote that is the x-axis. Okay, so now this is the part where we kind of digress, and you guys don't necessarily know a whole lot to start the next part. But this is, this is more, you might work on it later in pre-cal some, but it's more calculus level, where that's where we talk about more. But the idea, because this is a positive function up front, we're going to start positive on the positive side of the x-axis at the right. Now, because I have this horizontal asymptote, I'm going to run alongside of it, yes? And I'm not going to touch it. But then what happens when I approach 2? Yeah, we've got this vertical asymptote, so I have to go up. And so the first part of my graph looks like such. Because as my graph is going to go off to the right, it's going to run alongside the x-axis. That's something called end behavior, which we'll get to on the next part. But it's going to run along the x-axis. When it hits 2, it's going to run up and along 2. It can't actually touch 2. Now, another piece is that when you hit a vertical asymptote, unless there's a reason to stay up here and stay positive, vertical asymptotes tend to change your sign. So here we finished positive, so that means down here now I'm going to be in the negative. So down here, it's running along the x-axis on the other, or not x-axis, x equals 2, the vertical asymptote. Now, this is where horizontal asymptotes are a little different, because the next asymptote I want to run along is -1. Horizontal asymptotes, you can actually cross through the middle of them, and I think it crosses through 0, 0 here, if I recall. Yeah. And so this actually will kind of curve and go up, kind of like your x cubed function, but it'll look something like that. Again, we've got another vertical asymptote. So since I ended positive, I'm going to flip down here and start negative. This time, the difference is when I get up to that x-axis, we have that horizontal asymptote that I am not crossing as I go out to the left here. And so it runs along the underneath.
What in real life makes graphs actually look like this?
And if I graph it on the calculator for you, I feel like it makes it hard to read there too. Looks something similar?
Yeah.
And I keep telling you guys, I want you to be able to figure out asymptotes algebraically, but I also want, can you see the asymptotes graphically? I mean, you can see looking at that, there's definitely something happening at 2 and at -1. You can also see as this graph runs out all the way left and all the way right, my graph is running alongside the x-axis. Okay? Yes?
So like outside of the math classroom, you use these kinds of graphs.
There would be places, more math fields though, probably. I don't have a specific example of where you would see it, but I would definitely see more of the like mathematical science fields.
I think that's what we use a lot.
They are definitely a little different. Okay, one last topic. End behavior. If you read here, end behavior is what is happening on the far left and far right of a graph. If there is a horizontal asymptote for the function, it will be approaching that number. So when we talk in behavior, I need you to think about your horizontal asymptotes. Because if there is a horizontal asymptote, that's what my end behavior will be approaching. If the graph is going to infinity or negative infinity, then it will approach that value. So, we talk about end behavior happening on the far left. I'm talking about, okay, as we go off over there towards Mr. Stanley's room to negative infinity. Or the far right of a graph. We go over to the far right towards Miss Minnick's room. Okay? That's what we're talking about. So, these 3 examples ask us to determine the end behavior. What did I say I want you to think when it says end behavior? We're going to think horizontal asymptote. And I can use the graph to help confirm that for you. Okay, so look at A. Determine the end behavior. So what is this graph doing as it goes off negative infinity and positive infinity? What do you notice in terms of horizontal asymptotes?
Biggest power on the bottom?
He says biggest power on the bottom, yes? Okay, because if we look at the biggest power on top is 3x. Biggest power on bottom is x squared. And even if you reduce this, so if I reduce this and I could cancel out an x, you're still talking 3 over x, aren't you? Biggest power is always on the bottom. Think about this, okay? As I start putting in bigger and bigger numbers for x, so like as we go off to positive infinities, I start putting in bigger and bigger numbers. 3 over 10. Well, that's 0.3, right?
Yep.
3 over 100. Now we're at 3 100ths. 0.03. 3 over 1,000. 3 over 10,000. What's happening to that number every time? It's getting smaller and smaller and smaller. And what is it approaching? Getting closer and closer to 0. Thus, that end behavior of y equals 0. Here's the graph. Do you see that horizontal asymptote of y equals 0? Okay. On the left, it's on the bottom. My graph is running underneath it. On the right, it's running over it. And as my graph goes out to the edges, my y values are getting closer and closer to 0. So thus, y equals 0. Okay, what about B?
And
Okay.
which would be 3 and 1.
Biggest powers are 3x squared and x squared. So biggest powers are matching, right? Essentially, if you cancel out your x squareds, it's 3 over 1, which is 3. So that means as my graph goes off to the left and off to the right, the y values are approaching 3. Okay, Keaton was talking about these other graphs being weird. Here we go. Well, maybe this one isn't as weird. It doesn't have breaks in it, I guess, but does in behavior of y equal 3 make sense here? As my graph goes off to the sides, where is it running alongside? It's running right alongside that 3 line. Did you have a question, Ethan?
Why does it cross the 0, like, when you have a horizontal asymptote?
Because horizontal asymptotes are a little bit different than vertical asymptotes. Like vertical asymptotes will never cross them. Horizontal asymptotes you can cross in the center, like in the middle area, just not out at the ends, like as it's going off to infinity. Okay, so horizontal asymptotes are more about the end. Because technically, I mean this one would actually, oh, that's not even a horizontal asymptote, so never mind. Sorry. Does that answer the question though? Yeah, and I know, what have you always been told about asymptotes? We don't cross asymptotes, right? That rule is more specific to vertical asymptotes than horizontal asymptotes. Horizontal, you just don't cross them out at the ends. You can in the middle. Okay, C. Ooh, I just looked at the time. Okay, what do you notice about C?
Power on top.
Okay.
There's no horizontal.
Biggest power on top, meaning in terms of asymptotes, there are no horizontal asymptotes. Are we agreeable there?
Yes.
Now, is this question technically asking about horizontal asymptotes? No, it's asking about end behavior. So think, if we look at the largest powers, 3x cubed over x squared. You can cancel how many x's? 2 x's, so then you have 3x over 1, which is just 3x. Your end behavior on this one is y equals 3x. Your end behavior is not a horizontal asymptote this time. It's a diagonal asymptote, which I know brings in a whole nother world here. But let me key this up real quick. Okay, so here's the graph. Maybe. Very slowly. Okay, this is what the graph is. Can you think of what the line y equals 3x looks like? Think y equals 3x plus 0.
Yeah.
Intercept 0, slope of 3. Let me help you. Here's the line y equals 3x. It's going to graph right through the middle of that. What is my graph doing? It's running alongside that diagonal asymptote of y equals 3x. So we don't deal with them a whole lot, but there is something called a diagonal asymptote also. And that's what happens when there's no horizontal asymptotes. Okay? There's no asymptotes when we don't have fractions. Okay? Notice asymptotes are happening when there's fractions involved. So homework. If you haven't already done or looked at it, page 95, numbers 48 to 66, evens. Do that for tomorrow. We'll check that tomorrow, and then we'll start going through our lesson 1-3 notes. Okay?
Sorry, did you get both of mine?